Have you ever wondered about the invisible forces that are, just all around us all the time? Well, today we're going to pull back the curtain on the hidden physics of fluids. We're talking about the secret language of liquids and gases that lets us do incredible things, like stop a car with just our foot or lift a massive airplane into the sky. All right, let's dive right in.
I mean, think about it for a second. It just doesn't seem possible, right? A simple press on a pedal, a tiny bit of force, and somehow that brings a massive, speeding chunk of metal to a grinding halt. It really feels like some kind of magic, but I promise you, it's pure, beautiful physics. And that's the very first puzzle we're going to solve. And here's a great look at the setup. You can see your foot pushes the pedal, which applies a pretty small force to that little piston in the pedal cylinder. But that push travels through the brake fluid, and on the other end, at that much, much larger wheel cylinder, that little push has been magnified into a huge one, strong enough to clamp down and stop the car in its tracks. So how on earth does a simple fluid pull off this incredible force-multiplying trick? Well, the answer starts way back in the 17th century with a genius named Blaise Pascal. He was the one who figured out the secret of static fluids, which is really just a fancy term for fluids that aren't moving around. It all comes down to pressure in a contained liquid or gas. So here it is, the official definition. What Pascal figured out way back in 1653 is that if you've got a fluid in a sealed container and you apply pressure at just one spot, that pressure isn't just felt right there. Nope, it's transmitted equally, everywhere, all at once, throughout the entire fluid. And here is our very first trick to help you remember this forever. Just lock this phrase in your head. A squeeze is shared everywhere. That's it. That's the heart of Pascal's principle. Any little push, any change in pressure is instantly shared by every single bit of that fluid. Okay, so this is how we actually use that shared pressure. Remember, pressure is just force divided by area. So if you apply a small force over a small area, you create a certain amount of pressure, and since that pressure is shared everywhere, it also pushes on that bigger piston. But here's the kicker. To keep the pressure the same over a much larger area, the fluid has to push with a much, much bigger force. That's the magic. Small force in, giant force out. Let's put some actual numbers on this, because this is where it gets crazy. A pretty small 500 Newton force on that pedal cylinder, that's about what a 110-pound person would exert just by standing on it, gets sent through the fluid. But because the wheel cylinder has a much bigger surface, that same exact pressure generates an unbelievable 12,500 newtons of force. That is the raw power of Pascal's principle. And that is how your foot stops a car. So that's the magic when fluids are just sitting still. But what happens when they start moving? Let's get into the really cool world of fluid dynamics and see what happens next. So the first rule for moving fluids is called the continuity equation. It sounds complicated, but it's based on a really simple idea. What flows in must flow out. If you've got water flowing through a pipe, the amount of water passing any given point has to stay the same, right? It can't just vanish. And boom, here's our next memory trick. Squeeze the hose, faster it goes. I know you've done this. You're watering the garden, you put your thumb over the end of the hose, you make that opening smaller, and the water shoots out way faster. That's the continuity equation, right there in your backyard. A smaller area forces a higher speed. Now, this leads us to probably the most important and honestly the most counterintuitive idea in all of fluid dynamics, Bernoulli's principle. It's the link between a fluid's speed and its pressure. At its core, it's really all about conserving energy. Think of it like a fluid has an energy budget. When it speeds up, it gains kinetic energy. That's the energy of motion. But that energy has to come from somewhere, so it pays for it by taking from its internal pressure. So more speed means less pressure. Now, this exact idea is a huge sticking point for so many people learning physics. Our intuition really, really wants to lead us in the wrong direction here. So let's just tackle this common mistake head on. Take a look at this diagram. You've got a fluid flowing along, and the pipe gets narrow in the middle, and then it widens out again. Now, based on everything we just talked about, start thinking, what's happening to the pressure in each of these sections? So here it is, the big question. Where is the fluid pressure the absolute lowest? Is it in the wide part, pipe 1? Or is it in that narrow, squeezed part, pipe 2? Now be honest, your gut is probably screaming that where it's squeezed, the pressure must be higher. But is that right? Well, if you got it wrong,
don't worry, you are in very, very good company. Research actually shows that a massive 66% of students have that exact same misconception. They think the pressure is highest in the narrow part. This is one of the trickiest ideas in physics, so let's nail it down for good. And here's the payoff, our third and final mnemonic: fast flow, pressure low. Remember our hose? Squeeze the hose, faster it goes. So in that narrow section, pipe 2, the fluid has to speed up. And what did Bernoulli tell us? Where the speed is highest, the pressure is lowest. It's that simple. Fast flow, pressure low. So there we have it. We've got Pascal's principle for fluids that are sitting still and Bernoulli's for when they're moving. That's our whole toolkit. Now let's see how these aren't just equations on a chalkboard, but are actually the forces shaping our entire world. This is so cool. On the left, you've got a hydraulic lift. Using Pascal's principle, a little force creates a huge lift. And on the right, an airplane wing. The air has to travel faster over that curved top than it does on the flat bottom. And what did we just learn? Fast flow, pressure low. So you get low pressure on top, high pressure on the bottom, and that difference creates lift. Two totally different principles, both using fluids to defy gravity. Now, just a quick reality check here. The principles we've been talking about are usually explained using ideal fluids, this theoretical idea of a fluid with no internal friction or viscosity. Real fluids, like the water in your glass or the honey in your tea, they do have viscosity. So these equations give us a really, really good picture of what's going on, but in the real world, things get a little bit stickier, literally. And I mean, the applications are just everywhere you look. A spinning baseball or cricket ball that curves through the air, that's all Bernoulli. How soap helps water clean your clothes? That's about fluid properties. And the absolutely vital flow of blood through your body? It's all governed by these exact same rules of pressure and flow. It's all fluid dynamics. This quote just sums it all up perfectly, doesn't it? We've seen that this area of physics isn't some abstract thing for a textbook. It's the invisible architecture of our daily lives, working silently and powerfully in everything from our own bodies to our most incredible machines. So I'm going to leave you with this question. Now that you have the keys, as squeeze is shared everywhere, squeeze the hose, faster it goes, and fast flow, pressure low, start looking around you. What other bits of everyday magic can you now explain? Keep asking those questions, and I promise you will start seeing physics absolutely everywhere.